Hello everyone. I hope in the lecture 1 you enjoyed in learning the Zeeman effect, in which we learned the normal Zeeman effect, its theory, and we also learned to draw the Zeeman pattern. Now in this lecture number 2 we are discussing the anomalous Zeeman effect, and we will also learn how to draw its Zeeman pattern and Lande G factor we are going to calculate in this presentation. First of all, let's recapitulate the previous lecture number 1, in which we discussed the normal Zeeman effect. The first point is in the normal Zeeman effect, we saw it agrees with the classical theory. Second point is in the normal Zeeman effect, the spectral lines are going to split into 3 lines. Another one is it is shown by the atoms having orbital angular momentum only. It is shown by the atoms whose spin angular momentum is equal to 0. It is also, we saw it is also applicable to the atoms having 2 valence electrons, and these 2 electrons are oppositely oriented, that is having S it is equal to 0. We also come to know about how to write the Zeeman pattern and the selection rules which decide the transitions to be allowed or to be forbidden, and at last the energy of each state that is given by this formula. Now we are going to start the anomalous Zeeman effect. Like in the normal Zeeman effect, the splitting of the spectral lines is in 3 lines, and for that S it is equal to 0. In the anomalous Zeeman effect, the splitting of spectral line of an atom having non-zero spin angular momentum in the presence of magnetic. And this is a bit complex than normal Zeeman effect. This anomalous nature of the Zeeman pattern is due to the spin of electrons. First of all, we will try to learn the Lande G factor. What is Lande G factor and how we will derive its formula, and then for various energy states we are going to calculate the value of G. For that, let us consider an atomic level specified by intrinsic configuration and the values of the angular momenta L, S and J. In the absence of field, its energy is E naught and having 2J plus 1 fold degenerate. When placed in weak magnetic field B naught along Z-axis, the interaction energy is given by E naught. It is equal to minus bracket mu L plus mu S bracket close dot B naught. Now, let us discuss this formula. In the previous case, in the normal Zeeman effect, this interaction energy is equal to minus mu L dot B naught, because in the previous case S it is equal to 0, which makes the spin angular momentum 0. In the anomalous Zeeman effect, we are considering the spin angular momentum also. That means the angular momentum uh, and that means the magnetic moment which is coming out to be the coming due to the spin angular momentum is also involved here, where mu L it is given by this formula minus E over 2m L vector, and mu S it is equal to minus E over m S vector. In this equation we multiply it by 2 and divide by 2. So we substitute the value of mu L and mu S in the, we are going to substitute this value and this value at the place mu L and mu S. After substituting these values here, in the delta E equation, we got the interaction energy that is given by this formula. Okay, so this is equal to delta E, it is equal to E over 2m L vector plus 2s dot B naught. Now, in the weak magnetic field, we know that J it is equal to L plus S. Now, this LS coupling will be very strong, and therefore we cannot break L plus 2S term into two terms. Okay. Now, based upon the quantum mechanics, we write L plus 2s equal to Gz, where G is a constant known as Lande G factor, and the value of G depend upon the energy state. It is different for different energy states. Now take the dot product of this above equation with J on both sides. We are going to take the dot product on both sides. So here we got J dot J, which is equal to J square. Now let us mark this equation number 1. Now this operator, that is J L plus 2s, this operator can be solved further. Now what we do here, in this we break in, we write 2s as S plus S. Now this L plus S is known as J. We take the dot product of this J dot with J. We got J dot J and J with S, J dot S. J dot J, it is equal to J square plus J dot S. Now, after that, as we know the LS coupling formula, L plus S, it is equal to J. From that, L it is equal to J minus S. Okay, and from this, L dot L, from this equation, as we know that L it is equal to J minus S, we got L dot L, J minus S dot J minus S. We can do it. It is very easy to do. So take the dot product, we got J dot J, J dot S, S dot J, S dot S. This J dot S and this S dot J, as the dot product is commutative, so these are equal and these get add up. And this J dot J is equal to J square, and this S dot S is also equal to S square. Okay, so that we can write. Now on solving this, we got the values. This become L dot L become L square. This J dot J become J square. This S dot S become S square, and these two terms get add up, that become 2J dot S. So that further reduced to, using these equation, we got the value of J dot S, it is equal to J square plus S square minus L square over 2. And from the above equations 1 and 2 and 3, we got the value J square plus S square minus L square over 2 is equal to GJ square. That is the new equation known as equation number 4. From this equation, we further solve it, and what we do, we're going to take the average of this equation number 4. Let us again write the equation number 4, because here we want to learn one thing more. See this J square. If I want to calculate the average value, what we do, this is J square, that means J into J. We will replace 1J by J plus 1. Here J square can be written as J into J plus 1. Similarly, this J square can be replaced and this s square, it is equal to s into s plus 1, and this l square is l into l plus 1, and again here is the j square. Okay, so that reduces to here j square can be written as j into j plus 1, this j square, this s square, and this l square 2 is as such. This j into j square is written as j gj into j plus 1. Now we are going to multiply both sides of this equation, that is equation number 5, by h cross square. Okay, h cross is h over 2 pi. So let us multiply this equation by h cross square. Here multiplied, here it is multiplied, and here it is multiplied. Then we got the new equation, and we divided this equation by j into j plus 1. So here we divided, here we divided, here we divided. So this term, this whole term get cancelled with this. Similarly, this h cross cancel with this h cross. Similarly, this whole term got cancelled with this. On solving it further, here we got 1. On solving, if we carefully see this factor become 1. Here, j to j plus 1 remain as such, s into s plus 1 remain as such, l into l plus 1 remain as such, over 2j into j plus 1. That is equal to g. So it is written in this left side. So let us designate this equation number 6. So Linde factor, this is the Linde g factor, which is a dimensionless number, and it vary from state to state. So that is about the Linde factor. Now, after learning to calculate the expression for the Linde factor, we're going to learn the spreading of the energy levels in the magnetic field. So, you know the theory I have already explained in brief. Now, in this case, the external field is small. So, due to the smaller value of the magnetic field, spin orbital coupling is dominated here. Okay, so that we are going to calculate. First of all, I will write the interaction energy. So interaction energy is given by the formula. It is also written in the previous slides. That is this mu j. We had written this mu j. It is equal to mu l plus mu s, because here uh, angular and spin, both momentums are counted. So whenever we remove this dot, so it is j b dot cos theta, and the value of this mu j is equal to uh, eg over 2n into j. Okay, where theta is the angle between the mu j and b naught, that is j and b naught. Now since this cos theta, it is equal to z component of j over j. Okay, that is written. After that, the value of this z component of j, it can be written as mj into h cross.